Log on, tune in, find out. Another good idea from Cambridge.
Presentation. Here I recall the basic formula which we have derived. Point z is in D if and only if this function, so you sum up the Fourier coefficients of this special function Vz with respect to the eigenfunctions of the far-field operator, sum up, square, divide by the eigenvalues, and if the series converges, that is a criterion. This is a binary criterion I mentioned. No? You can decide yes or no, convergence or no convergence. And if we write it in this way also, and then you see that the sign of W is just the characteristic function of D. So you have an explicit formula for the characteristic function of the domain D. And I have prepared now a MATLAB program. I hope that it works. Okay, so what is the what do we have to know? First of all, this is an infinite dimensional setting in function space. In practice, you have only finite many data, so instead of the far-field operator, you have a matrix consisting of the kernel of this operator. Okay, so you have a matrix, and in that case, a square matrix, and what you do is you compute now the eigenvalues and eigenvectors of the matrix, you store that, and then you, instead of the series, you compute the sum of what you have just seen on this last slide. And that is what we plot just. And so let me, so first of all, you know MATLAB, no? So no variables here. So now I load an example, and what you see here are, I hope that you can read that, maybe you can put it bigger, I don't know. You can. FF is a matrix of size, let me see, size FF of size 120 times 120. So these 120 incident waves, 120 directions of observation. That is what I have computed by some code, integral equation or code, but this is given. And Ka is a wave number. Ka is a wave number 5 here. Okay, so I don't have only this information. I don't know the model. Is there a Dirichlet boundary condition? Is this really an inhomogeneous medium case? Is this, could be. So that is my information now. And what I do is I compute this W. From this information, I can compute this function W I've shown you. Okay, so first of all, I run this is my forward data. I want to say, okay, 120, that is too much. I use only 32 times 32. And I could add error, random error. I put no error here to show you the best result. Okay, and now why do I have oh, okay, 32 is wrong. It must be, you must divide 120 by this. So I have to do it again, sorry. Data, here I to say 30. And okay, now I run my factorization method on that, and I have to tell them the region which I have to discretize. Now I have to choose the point Z, and so I put a square around that, and for every Z in a grid, I make this test. I compute this W. So my region, since I don't know, I choose a pretty big region, minus 10, 10, minus 10, 10. And now it works. And what I see is this. You see, that is really, that is the actual computation, what I've done. you see what looks like artifact there. You see the you see the grid. No, it's a pretty coarse grid. For all of these grid points, I have computed the function w and plotted the function, you know, in this color plot. Okay. Now my code, what it does, it refines the grid, and of course here I don't have to refine it here, but just around this the obstacle. But already here you see apparently my scattering object consists of two parts, no? This and that. Okay, so I do a refinement, and so I see it already better, and I can go further on that. But I don't do that here now. I quit that, and I clear everything. I want to show you another example, and close all. I don't know. So I load my, say, I don't know, maybe third example, and I do the same thing. Oh, 36. So I take the 36 and don't add that, and now I let the same region there. I think I can go back here. Okay. So I now, because I didn't know myself what kind of example that was. These are real data, actually. These are real data. A couple of years ago, or maybe 15 years ago, some engineers put the measurements of something into the internet and asked the community to run the favorite codes. You know, they did not tell us what the obstacle was. They told us the wave number, and they told us that this object is made from aluminium. But we don't know we don't have to know that in this part. So I run this, and it comes out, and then a year later they published the result. It is an aluminium triangle, and you see fairly well that it is correct. Okay, and also the demonstration should show you how fast this method is. You know, I mean, the computation of the inverse problem, you have seen that, no? And I finish now this this little demonstration here. So maybe exit here and go back to my slides. I have done now a couple of more numerical simulations, but I show you just the pictures now. Okay, so we had that already. So the following examples, I should have done that before, show you the finite dimensional case, of course. So this is with directly boundary condition. No, what I showed you was a little bit more impressive. This was no noise, here a little bit of noise. And this is the wavelengths here. These are kind of two, again, directly boundary condition here. I guess I have put 5% noise there. I'm not quite sure there. But here you see them very clearly. Here, yeah, okay, you can evaluate that yourself. This is scattering by an open arc. I didn't have to know whether that was an obstacle or an open arc. No? The far-field pattern is just a matrix in the finite dimensional case, wave number, and here I did the code, sorry, and no error, and that is 1% error only. You see, a very sensitive noise there. So you cannot really distinguish here, is that an arc or you know, a region positive measure. This is the real data. Now this was this aluminium triangle. This is a plexiglass triangle. Aluminium is modeled by directly boundary conditions. Plexiglass is modeled by an inhomogeneous medium that's going inside. Now a three-dimensional case. This computation has been done by Kleefeld from Cottbus. And that is kind of interesting. I want to go into a little bit into that. Here you have a Helmholtz equation inside and outside of D. D is, in this case, maybe such a body here. It's a transmission problem. So you have the Helmholtz equation inside and outside. You have the Dirichlet data coincide from inside and outside. And the Neumann data, that yeah, they jump, and the jump is proportional to u on the boundary. So these are called conductive boundary conditions, modeled if you have a very thin layer on top of the obstacle with high conductivity, then this is modeled by that equation. So here you see lambda equal 1, you get, I can tell you pretty good reconstruction there, but the interesting plot is this one. This one is lambda is 1 on the upper side and 0 on the lower side of the ball. That is just the unit ball there. Yeah, if lambda is 0 on the part of the boundary, say on the lower part, then you have Dirichlet and Neumann boundary condition coincide on that part, and that means the solution is analytic through that part. So it's really scattering by a half sphere, you know. No, it's sufficient if you have Helmholtz equation inside and outside, and Dirichlet and Neumann condition coincide on that part, then it's analytic through that part. So scattering by a half ball. And I did not know this lambda, of course, before. I had just the matrix of the far field pattern, but here I actually see only the upper part, which is absolutely correct. I could not determine the lower part because that is not, there's no scattering by this lower part anymore. Okay, so this was the factorization method, and briefly, at least last half an hour, I want to show you a little bit on this interior transmission eigenvalue problem. That came up as an assumption. K square did not have to be an eigenvalue of this interior transmission eigenproblem. You know, remember this was the one differential equation, that was the other differential equation, and the Cauchy data coincide on D. And I might make the assumption here that Q is positive and bounded below everywhere on D. This is called interior transmission problem because both equations live in the interior, and apparently it's an eigenvalue problem. Next week there will be a talk by John Sylvester. He weakened this condition. Q only in his talk had to be bounded on the neighborhood of the boundary, but inside could be arbitrary, change sign, and so. He will talk on that. The question is a set of eigenvalues discrete? Do eigenvalues exist? Yeah, first the radially symmetric case. Also there will be, David Colton will talk on that case next week. And so if you have a ball of radius a and your function depends only q on r, and here you have an assumption that the q is not 0, but in general q could be bigger or smaller than 0, but this mean does not have to be 1. And by a standard transformation of Liouville type, you get an ordinary differential equation now. Yeah, for y, and yeah, w satisfies the ordinary Helmholtz equation, so it has to be some Bessel function as a solution. So this is one of the Bessel functions here, first one. Okay, and now you have w and u of that form, and you have now two parameters, alpha and beta, and if you match the boundary conditions, you have two boundary conditions, Dirichlet and Neumann. That gives you two equations for the two unknowns, alpha and beta. And you want to determine when this system does not have a trivial solution, so you look at the determinant as a function of k, and then you can do the asymptotics of that y when k tends to infinity, and that gives you really indeed a sequence which goes to infinity. So that is a long time ago. That was discovered already. The spherical symmetric case, you have eigenvalues and they are discrete. Now the also you see it's pretty old stuff here. You see the asymptotics even of the wave number, and also Joyce McLaughlin did also the inverse, something about the inverse spectral problem for the spherically stratified case. Okay, a uniqueness problem, but I You can, till 2007, there is a survey paper on that. Now we want to look at the general case. If you look at the difference between W and U, call that V, then the Cauchy data of V vanish on the boundary, because they coincide, the Cauchy data there. And if you set up the differential equation for V, then you can come up with this inhomogeneous equation. Right? Somehow V corresponds to the scattered field, is also this inhomogeneous. Okay, now you divide by Q, get this equation. We assume that Q is positive. John Sylvester cannot do that, because if Q changes sign, then you cannot do that. That's the point. And then we know that W has to solve the ordinary Helmholtz equation. So we apply the Helmholtz operator to this equation. We get a fourth order equation for V. Fourth order equation for V in the space of those functions in H2 with Cauchy data 0. And then you can show easily that K is an interior transmission eigenvalue if and only if you have a solution of that equation which is not trivial. So okay, there's a standard approach there. The weak form is you take a test function in the same space and do Green's theorem. This is a weak form. You define an inner product here in this space with this boundary condition. It's appropriate to take this as an inner product, which is equivalent to the ordinary inner product there. You see, I speed up a little bit because and then this is a bilinear form with respect to V and psi. And if you collect you have one part, 1 over Q delta V delta psi, and then you have parts with K square, 1 over Q, 1 plus Q V delta psi, and then there's one with 1 over Q psi delta V, these are there, and then there's one part with K fourth, K square times K square, that is this part, 1 plus over Q, this part. This can also be written in this way, a little bit simpler here. Yeah, because here you see A2 is symmetric, apparently, and A1 is also symmetric. This is symmetric. If you interchange V and psi, it gives you the same. And if you change V and psi, that also gives you the same by Green's second theorem. If you can put the Laplacian on that, it's the same, because the boundary data of psi and V vanish on the boundary of D. So this is a self-adjoint forms here. And I do it the following way by this. I use a representation theorem of Ries. If you have these bilinear forms, then you can transform that into operators in the Hilbert space. So you have then K1 belongs to A1 and K2 belongs to A2. You have then operators which are self-adjoint operators, and then this variational form just takes you to this eigenvalue problem. If K square is the eigenvalue, then it's a quadratic eigenvalue problem. Yeah, if you call K square lambda, then lambda plus lambda square. And there's one way, there's a standard K1 and K2 are self-adjoint. Also, K2 is positive, therefore you can define the square root. They're also compact operators. And if you set Z to be K squared times this V, then you end up with the system, which is now an ordinary eigenvalue problem there. But as you see here, and that's the reason why I put it there, you see it is not self-adjoint. The operators K1 and K2 are self-adjoint, but here you have a minus sign. And it is not only because of the presentation here, it is really the case. Recently it has proven that in special cases there indeed exist complex eigenvalues. So the problem cannot be self-adjoint. But from this approach, you immediately see that answers question 1. The spectrum is discrete because these operators are all compact here, and this is an ordinary eigenvalue problem for a compact operator, right? So there are now, I mean, kind of, you see, very old paper there here in the 19th, and you see here, yeah, okay. This very recent result of John Sylvester, and he will talk on that next week. No, I cited that here already. The question of existence has just been answered positively a couple of years ago. There was a long, I mean, there were 20 years of thinking, and people could not do the existence proof, and now it turns out it's very simple, or really simple. It's really astonishing that we did not find this answer. Here, and you see, 2008, Paverin, I think Sylvester had they both discovered the idea in an Oberwolfach conference I was organizing. So they found the basic idea how to prove existence in this conference, and under pretty strong assumptions, or under assumption on the contrast, and they, with a very nice idea, dropped that assumption and showed it for a very general thing. The idea is the following. We consider this operator pencil, I think it's called operator pencil, depending on this parameter tau. Tau was this k square. Okay. Now the goal is you have to find tau and some v which is not 0 such that that is 0. No? That is the goal. Then you have found this eigenvalue. A tau is self-adjoint, and the spectrum of A tau is discrete, and the eigenvalues depend continuously on tau. And they converge to 1 because, if you put tau equals 0, then you have the identity, and the eigenvalues of the identity are 1. Okay? So if tau is 0, then the spectrum is just consists of 1. The idea is now construct some tau such that the smallest eigenvalue of tau is negative. Then you have the situation for tau equals 0, it's positive. For some other tau, it's negative, this is the smallest eigenvalue. The smallest eigenvalue depends continuously on tau. That must pass through 0. So this is the idea. And this was again my A tau here again with the small with the bilinear form. You know, I had written that in this form here, but now for psi equal to v, so for this bilinear form. So you have something like this here and that. Here your q appears. Here there's no q anymore there. So now the idea of this is the idea of Peverinter and Sylvester, actually, and they constructed now a particular V such that this part is negative. But the Ciacconi, Drossos, and Hadda, they had a much simpler idea, and that's the following. We take now an open ball which is inside of D, and we consider the interior transmission eigenvalue problem in this ball B with constant contrast Q0. Q0 was the lower bound of Q. Now you are in a ball with a constant. Yeah, we know already. Yeah, and the corresponding bilinear form I denote by hat now. Yeah, so this was the original one with D, 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 and Q here. And for the ball with Q0, it is this, with hat there and B there. Okay. So we know already from the example I showed you for the spherical stratified case that for that case eigenvalues exist. Right? That was the reason why I had to show the example beforehand. Okay. So the example shows you there exists a tau hat and some V hat in this Sobolev space in the ball, such that A hat, tau hat, V hat is equal to 0. Okay. Now you extend V hat by 0 outside of this ball. Right? So V hat Cauchy data, directly, and Neumann data 0 on the boundary of the ball. If you extend that to 0, then a standard argument from Sobolev space theory tells you the resulting extension is also in H2 of D, of the bigger region, right? Okay, and then you look at that form and substitute for this tau hat and this extended version V hat. Then you get that. I mean, I just copied this with this. But this is positive, and Q can be estimated below by Q0. So you have this inequality here, and this does not depend on that. And you can, this is on D, but you can shrink it on B, because V hat is 0 outside of B. Also here you can shrink it to B, because V hat is 0 outside of D. Okay, but this is exactly this form here. And that is 0. So you have, for that V hat is less than 0. And you're finished. It's a typical example that you need long to get the proof, but then it's getting simplified, and at the end it's so easy that you can present it in such a talk here. Yeah, so now for this T hat, yeah, the smallest eigenvalue is less or equal 0, and the smallest eigenvalue for 0, that is equal to 1, is bigger. The continuity of the eigenvalues, yeah, on with respect to a parameter tau, if the operator pencil depends continuously on tau, gives you an existence of an eigenvalue. Now what they do is give me any m, number m. You can fit m balls into the region D. Yeah? If you make the radius small enough, disjoint balls. Then you can show that and take take an eigenfunction and extend each of them by 0 outside of that ball. That gives you a family of m functions, and they are linear independent. That and then you have a space of m-dimensional space, and you can do the same kind of arguments here and get that you have infinity many real eigenvalues, and also they can tend to infinity. No? So that was the result by Gendidis, Ciacconi, and Haddad. And this has now been transferred to other eigenvalue problems. This is the same idea. You can do the same thing. And one of my PhD students is looking at that case where you have a periodic structure, scattering by a periodic structure covered with a layer. Then it turns out that the corresponding eigenvalue problem is that you have Cauchy data coincide up and down, and you have periodicity condition to the right and left. And but there other questions also arise. Okay, just briefly mention also you can do the factorization method in AIT. I'm not going into that because time does not allow that. I just go through the formulation first of all. That is the classical problems in AIT, the weak formulation there, and existence and uniqueness. You have the Neumann-Dirichlet map. This space with the this one is mean 0 function because it's a Neumann problem. The constant function, the constant is always solving that problem, and also you have to have that f is has a mean 0, otherwise you have no chance to solve that. Well known, everything. Factorization method is now my conductivity is background plus Q. By the way, Liliana in the previous talk, she also had the kind of a background velocity, I mean for the scattering problem or for the wave equation, plus a perturbation. In my case, in my talk previous part and also in this part, the background is constant, 1. But also you can do that, the same kind of thing also if the constant is not 1, but is a function which you know. Then everything goes the same way. You have to modify though the Green's function. It's not the free fundamental solution anymore, but it's a Green's function with respect to this known background medium. But then everything goes through in the factorization method, and here too. And so the problem is determine D, where the contrast differs from 0 from this lambda. And here we work with a relative Neumann-Dirichlet map. So we look at the case lambda 0, where the contrast is 0, and at the difference there. And don't go through that. Yeah, sorry. Somewhere the factorization should be there here. So you get a factorization of the relative of the difference between background one. This is one you can compute. This is the one you measure, and you have a factorization in the same type there, and you get that also T is self-adjoint and coercive on these computations here. The range identity tells you the range of this is a mistake here. No? It's not T here. That is A star. No? The A star was the outer. A star is the outer one. T is. No? That is a typing error here. You get that. And now, what is a little bit more difficult to construct these function phi z. In the scattering problem, it was just the exponential e to the minus ik, which is the far field pattern of a point source sitting in z. Here you have to use the Green's function with respect to Neumann boundary condition on the boundary of B. You take the Laplacian in B and you take the Green's function, but with the almost homogeneous boundary condition on B. You're not in an infinite dimensional. In free space, it will be the fundamental solution, but in this ball, it should be the Green's function there, and then you define Vz to be A. A is a fixed vector times the gradient with respect to z of that, because then you have 0 boundary data here. And then you have the same kind of result as we had before for the scattering problem. Okay, finally, just some literature. As I mentioned already, in the second edition of my book, I included this part here on the impedance tomography. Did also something about the direct problem there, linearized problem, Calderon's original proof of uniqueness for Q itself, not only for the domain of the support, but for Q itself. This nice, which is the basis of actually is the basis of what Andreas Nachmann also told us, the origin. And also we have published a book on the factorization method for this kind and other types of inverse problems. And just the final remarks, you can apply the factorization method always if you have the matrix or the far field operator and the wave number. Then you can just numerically do it. The other point is it justified? Can you really prove that z is inside of d if and only if this function belongs to the range? No? And unfortunately, this has not been, or fortunately, this has not been answered so far for all of the problems. It has been justified by this kind of problems. Also, no, you don't know, is this equation this type or the other type? Scattering by elastic waves, scattering by arcs, periodic structures, and waveguides. And recently, Armin Lechleiter did it for the nonlinear Helmholtz equation also, which is kind of interesting because the arguments all rely on linearity here, but he did it for the nonlinear Helmholtz equation, and recently, together with Hada, also for the full wave equation. And he will talk on that next week when he comes. The case which we cannot cover is the following. A very simple case. You have two obstacles, one with Dirichlet and one with Neumann boundary condition. Yeah. Then the operator, you can set up the factorization, no problem. But the inner operator T is not coercive anymore. Yeah, it is, so to speak, positively coercive on the part which comes from the Dirichlet boundary condition, and it's negatively coercive on the subspace which comes from the Neumann boundary condition. So it's really a difference of two coercive operators, essentially, plus a compact perturbation. You know? And so we don't know what happens there. Or if you look at the inhomogeneous medium case, Q, if on part of the Q, which is somebody here, which is a lung, if the lung has a lower conductivity and heart has a higher conductivity as a salt water, you know, the background medium, I remember his tank. This is the case, yeah, where on one part it's lower and the other part is higher. We also cannot be settled. It's the same kind of thing. On one part it's positively, on the other part it's negatively coercive. So it is really, numerically, it works. Yeah, I mean, you get the same results, they are as good as these ones. But the mathematical justification of that is still an open question. And okay, so I think this is all I want to say. I thank you for the attention, and yeah, that's it. Open for questions, of course.
Are there any questions for the moment?
So you've made a few brief remarks about factorization for EIT, and then you've got to construct these functions phi z, which seems to involve solving as many Neumann boundary value problems as you have points z. And that sounds quite expensive.
Yeah. Okay, so what we did in numerical simulations was that we took a ball. B, the notation already indicates that for a ball you can write down the Green's function explicitly, and your phi z is it's just a times x minus z over x minus z absolute value or square or something. For there you have it explicitly, and then you can do it. But you are absolutely right. But also if the background is not one, where you have the fundamental solution, but as I mentioned, if you have a non-constant background, then you are right, for every point you have to compute the Green's function. That will of course increase the numerical amount. On the other hand, in the AIT program, if you have the Neumann to Dirichlet data operator, then you can express that. You can use that to compute the Green's function there also on the boundary. You can. I have to think a little bit, but no, you take the fundamental. No, the Green's function is a perturbation, smooth perturbation of the fundamental solution, and the boundary values you can compute by the Dirichlet-Neumann operator itself on the boundary, and that is what you have. So you don't have to compute it, but nevertheless, it's more expensive than in this case.
Further questions? I suggest we make then thank you very much again for the whole